In this video, let us come up with with the basic postulates of old quantum mechanics, and give the brief description of those basic these basic foundations. The Planck's quantum hypothesis. In 1900, Max Planck proposed the idea that energy is quantized in discrete units called quantas. This was a groundbreaking departure from classical physics and led to the development of quantum mechanics. The next important point is the black body radiation and Planck's law, and and this the Planck's quantum hypothesis explained black body radiation, the electromagnetic radiation emitted by a perfectly absorbing and emitting surfaces, by assuming that energy is emitted and absorbed in discrete units or quantas. Then the next one is the photoelectric effect and Einstein's explanation of photoelectric effect. The photoelectric effect was observed when light strikes a material and releases electrons. It was explained by Albert Einstein in 1905. He proposed that light consists of, of discrete packets of energy, and the energy of the photon determines whether it can release an electron or not. Then comes the Bohr model of hydrogen atom. In 1913, Niels Bohr proposed a model of hydrogen atom based on discrete energy levels. Electrons could only occupy certain orbits or energy levels around the nucleus, and the transition between these levels explained the emission and absorption of light. The next important foundation was the wave-particle duality and de Broglie hypothesis. In 1924, Louis de Broglie suggested that the particles like electrons could also exhibit wave-like behavior, extending the wave-particle duality concept to matter. This idea was confirmed by experimental evidence revealing the dual nature of material particles. Then the quantum theory of Rutherford's scattering. In 1911, Geiger and Ernest Mordison, under the guidance of Ernest Rutherford, conducted experiments that led to the discovery of atomic nucleus. Rutherford's theory explained the scattering of alpha particles by assuming a small dense nucleus and mostly empty space within an atom. The next foundation was Compton's scattering and particle wave interactions. Arthur Compton's experiment in 1920s showed that X-rays could interact with electrons as if they were particles. The phenomenon known as Compton's scattering supported the particle nature of photon and was a crucial piece of evidence for the old quantum theory. The next important point is the quantum mechanics and the spectral lines. The old quantum theory explained the quantization of energy levels in atoms, providing insight into the spectral lines, like Rydberg formula derived using these ideas. So describing the wavelength of lines in the hydrogen spectrum. And then comes the wave mechanics of Schrödinger and matrix mechanics of Heisenberg explanation. While the old quantum mechanics successfully explained many problems, it had its own limitations. I mean, it could not explain the fine details of atomic spectra, electron spin, and other phenomena that required more advanced theories. Now, these limitations eventually led to the development of the modern quantum mechanics. And this in the midst of the 1920s, two mathematical formulations of quantum mechanics emerged. One was Erwin Schrödinger's wave mechanics and Werner Heisenberg's matrix mechanics. I mean, these formulations were equivalent and provided a framework for understanding the